Welcome to Mastering Solutions. In this question here, now we have a diverging lens. And so this kind of arrow, how I've drawn it, this is typically how we will represent a diverging lens in a ray tracing diagram. And we're told that we have an object that's 20 centimeters in front of this lens, and the focal point is 10 centimeters. So here's 10 centimeters and 10 centimeters, and it's negative, meaning that it's a diverging lens, right? And so the object is 20 centimeters in front of it, so it's basically double, so we'll say about right there. And so now we need to use ray tracing to figure out where the image is going to be. And if you draw this very, very precisely and exactly to scale, you can see very accurately where the image is going to be. There were tests I had in optics classes in graduate school where they would give us graph paper and they would tell us, don't calculate anything, draw the ray tracing exactly and tell me exactly where the image is going to be. So it's definitely possible. We're not going to be that precise, but what we are going to do is, we've talked about in a few other questions, you need to remember three things whenever you're doing a ray tracing diagram. Remember parallel to the focal point, and then remember center of the lens, and then focal point to parallel. The reason is when you have parallel or collimated light, by definition, it focuses at the focal point. And by definition, if you have light coming from the focal point, when it passes through the lens, it will be collimated. And so we could have an infinite number of light rays coming off of here, but we need these three. These are the bare minimum that we need to show where an image will form with a lens. So let's start with parallel to the focal point. So we have a parallel light ray here. And now we're going to go to the focal point of the lens. But the problem is we have diverging light. And so instead of going to the F2, it's going to come out like this. So instead of going to the F2, it's going to come out like this. And so what we have to do is we have to extrapolate the light ray back as if it went through the focal point. So that's how you know how to draw the diverging ray out here. Now we're going to draw one from the top straight through the center of the lens. You do this for every single ray tracing diagram you do. And now we're going to do another one where we're going to go as if we're going to this other focal point over here, but then when it hits the lens, it's going to be collimated light. So I'll show you what I mean. If we had to go all the way through, instead of going through the center of the lens, it would go like that. As soon as it got right here, now it's going to be perfectly parallel light. So we have to extrapolate this back again. And so you can see I was off just a little bit, probably on my focal point distances, but you get the idea that the image will form right here. And so because we have a diverging lens, we will always have a virtual image, and it is going to be upright. And so that's the answer to the question, and we've done the ray tracing. I like to show you how to calculate it, even though they don't ask, just for practice in case your question, maybe they ask to calculate it. And so we're going to use the thin lens equation, of course, and that's 1 over f is equal to 1 over the object distance plus 1 over the image distance. We're trying to solve for the image distance, of course, so we'll minus over 1 over s. 1 over the image is equal to 1 over the focal length minus 1 over the object distance. And now when we put our values into the question here, we have 1 over the image distance is equal to 1 over the focal length, which we said was negative 0.1 meters. We're going to minus the object distance, which is on the upstream side of the lens, so it'll be a positive value. So 1 over 0.2 meters in this case for the 20 centimeters. That is going to give us 1 divided by negative 0.1 minus 1 over 0.2. And so we have negative 15. What is the values for this? The thin lens equation gives us the values of diopters, or how much light is refracted by a lens. And so we want this in meters, so we need to take the inverse, because that is, this 15 represents 1 over s prime. So we have because the 15 meters represents 1 over s prime, we need to take 1 over minus 15, and that gives us, in meters, negative 0.067. So when we move the decimal place 2, that is 6.7 times 10 to the negative 2 meters, or 6.67 centimeters, and that's negative, of course. So this is our image location. It's 6 and 6/7. It's 6.67 centimeters, and the negative indicates it's on the upstream side of the lens. So if the image is over here, it'll be positive. If the image is over here, it is negative by convention. So this is the answer. We have virtual upright at 6.67 centimeters.